Okay, in this video, or this is a part of a series on which I will show you e to the I pi equals -1, which is what I've written here. So at the beginning, you probably don't know what that means, but don't worry, that will be explained. So first, we're going to start with something you should know: the number 2. Everybody knows the number 2 is 1 plus 1. It's just this. This is 2. Okay. So we start with, let's say, what's 2 squared? Well, 2 squared by definition is 2 times 2, right? Which is 4. Okay. What's 2 cubed? 2 cubed is 2 times 2 times 2, right? Which is 8. Okay. And let's 2 more. I don't know. What's 2 to the 4th? That's 2 times 2 times 2 times 2, which is 16. And 2 to the 5th is 5 2's. So in general, if we want to raise something to a power, like 2 to the power of 5, like I've just done, that just means write it 5 times and then multiply them together. So this is what I've done so far: 2 squared, 2 cubed, 2 fourth, 2 fifth. So this follows from the definition of raising stuff to powers. Okay. So now what we're going to do is we're going to think. So you might notice, what would 2 to the -1 be? Well, the problem with doing something like that is, by definition, that would be taking -1 2's and multiplying them together, which doesn't make sense. You can't multiply -1 or something. So the problem here is that we can't define this. So we need to come up with a smart way so that this is defined. Okay. So how we're going to do this is we're going to use a cool property, which basically says that, so I'll show you what the property is. So if I'm thinking of some number, let's say 5, and then some other number, 3, doesn't really matter, then 2 to the power of 5 times 2 to the power of 3 is 2 to the power of 5 plus 3, which is 8. And you can put this into a calculator and you'll see that this is true. Okay, so what this says is that 2 to the power of something, in this case I chose 5, times 2 to the power of another thing, in this case 3, is 2 to the power of the sum of those two things. Now, why would this be? Well, what you might notice is that 2 to the power of 5 literally means, and I've written it here, 5 2's all multiplied together, right? That's 2 to the power of 5, which is this, is just this, okay? What's 2 to the power of 3? That's 3 2's. So if I multiply 2 to the power of 5 and 2 to the power of 3, I get 3 2's and 5 2's multiplied. That's just 8 total 2's all being multiplied by each other, which is exactly the same as 2 to the power of 8. Okay? So therefore, we have this rule, which allows us to now actually define raising 2 to the power stuff for all powers of 2. And how we would do this, for instance, if we wanted to find 2 to the 1.5, what we could do is, well, whatever that is, what's 2 to the 1.5 times 2 to the 1.5? Well, what is, by definition of our summing rule that we just talked about, if I have 1 and a half, I sum them, that would be 2 to the power of 3, by the rule we just talked about where the exponents are summed, and 2 to the power of 3 is 8. So therefore, because 2 to the power of 1.5 squared, or times itself, is 8, we see that 2 to the power of 1.5 is square root of 8. Okay, so now and there's some more little things you can do, but basically, so now we can raise 2, and it's not just 2, that's just the example I showed, but you can raise 2 to the, or anything to the power of any other thing, basically. Alright, so now what we're going to do is we're going to look at, and this is sort of the start of the main part, is we're going to look at 2 to the power of x. Okay, so if you haven't seen variables before, this just means I'm thinking of a mystery number x in my head, and I'm going to raise 2 to the power of that, okay? So now so if the mystery number x is 0, then this is 1. So if x is 0, 2 to the power of x is 1. And what this means is, if that mystery number x turns out to be 0, 2 to the power of x, well, that x was really all along just 0, so this would be 1. So if you haven't seen variables before, that can be a little confusing, but hopefully you have, or you can understand. So then the question we want to ask is, how fast is 2 to the power of x changing near 0? Okay, so what this means is 2 to the power of x, if you can imagine, if I plug in different values of x, it's going to output different things, and we want to find out essentially how fast the output is changing as we change our input. This is the idea of calculus. Okay, so you can think of it as a rate of change. It's the speed at which the output changes. Okay, it's just like speed. You imagine it's exactly like something like speed, like speed at which a car. It's basically how fast the car's position is changing. Okay, so that's what speed is. The same thing here, the derivative, or whatever you want to call it, the rate of change. So basically, what we're going to do is how we're going to find this is we want to find the rate of change of 2 to the power of x at x equals 0. Alright. Now what this means is if we're taking this as our function, you don't really have to know what a function is, but it's basically if x is set to 0 in this equation, this is going to be equal to 2 to the power of 0, which is 1, as I said. And then if we shift x a little bit, we want to figure out how fast this thing is increasing or decreasing relative to the amount we shift x. Okay, so and this amount is called the derivative at 0. And it's very important we specify where this is, because if we were talking about a different point as our initial value, you can think of it would be more or less sensitive depending on where that point is. So it's very important you specify. So right now we're talking about x equals 0. So I have 2 to the power of x, and I take x equals 0, and we're shifting x a little bit from 0, and we're measuring basically the amount is shifted relative to how much, the amount the output 2 to the power of x shifts relative to how much we change x, okay? So the way to figure this out, and the thing about calculus is you have to use very small numbers, so this would only apply if you, I guess the reason for this is because it's actually the output is changing, we're averaging it, but you don't have to worry about that. So basically, if we want to find the rate of change, what we do is we take 2 points, right, very close to each other, and we find the basically how much it changed in between those points, how much the output and the input changed in between those points, and then we divide the change in output by the change in input. All right, and the reason we do this is because this will basically tell us sort of relative to how much we change the input, how much the output has been changed. It's the ratio. It's all about the ratio in between them. We're dealing with very small numbers here, and they're both 0, so we're basically 0, very small, and so we have to take the ratio. So for instance, if I take so let's take one of our numbers, because we're interested in around 0, so we want both our numbers to be very close to 0. So let's say I'll take one of my numbers to actually be 0. That makes sense. So that means, so the first thing we're going to look at is if x equals 0, well, then we already said 2 to the power of x equals 1. So this is our sort of first x value that we're going to look at. Let me make it so you can see it more. Yes, okay. Then another one we're going to look at, remember, calculus works best with small numbers, or rather small differences. So if we're starting x value with 0, with small differences, let's say x equals our second point very close, 0.001. So we're only changing it a little. That's very important. Otherwise, you'll get some random thing. So just remember, use small values. The smaller the value, the better the answer will be. Alright, so then what would 2 to the power of x be? Well, you can just plug this into a calculator, or in theory, if you really have a thing for doing really boring long math, like just calculations, I mean, you can just calculate this using the method we talked about over here. If you can figure out how to do that, there's a way, but it's just really boring. But anyway, a calculator can really easily find this. Just remember, it's just 2 to the power of x, and x is 0.001. All you have to do is just 2 to the power of 0.001. We don't have to simplify it further for now, okay? Because the machine can do that for us later. So these are our 2 points. Remember, we want to figure out the rate of change. Basically, how fast 2 to the power of x is changing as we vary x relative to the amount we vary x. And the reason we have to do relative to that amount is because otherwise it completely depends on how much we're changing x by. Because the more we change x, the more output's going to change, because it depends on x. So it's just about sort of how fast it's changing. It's like the speed. Like, you don't measure speed by how far you travel. You measure it by how far you travel divided by how long it was. Okay. So now we have our 2 points, and what we're going to do is we are going to basically find the ratio between the outputs change and the inputs change. And this will tell us, you can sort of also think of it as how sensitive the output is to a change in the input. It's basically how much more or less the output changes for some amount we change the input. So like if I imagine wiggling the input a little and the output changes more, we could say it has a higher sensitivity. If I wiggle the input a little and then the output changes even less, then we could say it has a low sensitivity. Okay? So let's figure out what that is. So what we need to do here is we need to figure out how much did the input change. Well, that's not that hard. We went from 0 to 0.001. Okay, so that changed by 0.001. That was between our two x values, the input changed by 0.001. How much did the output change in between those two values? Well, our two outputs were this and this, so we just subtract them. That's the difference in between them. That's how much changed. So we get 2 to the power of 0.001 minus 1. This is how much our output changed. Okay, and then we divide the output by the input to get sort of sensitivity of the output relative to the input. Okay, and that would be 2 to the power of 0.001 minus 1 divided by 0.001, and you can put this into a calculator and you can compute this number, and it's about 0.69, maybe 693, I don't know. But the point is it's just some random number, right? It's nothing special. Okay, so we just chosen a nice number 2, and so we just gotten some random number as sort of sensitivity of 2 at 0. So the important thing to do now is to look at our number e. Okay, and if we look at the number e, remember, this is what we saw here in our original thing. If you just remember that from the very beginning, you might have seen the letter e. So now I'll explain what the letter e is. Okay, so first I'll explain the stuff you should already know. This is -1. You should know that. Equal sign pi. I'll talk about I later too, probably towards the end of this series. And then e is a number, sort of like pi. It's a letter that represents a number, exactly like pi. E represents a very special number, and you can actually define e as a number which has this property, where it basically, you saw how when we did this with 2 to the x, we got just some random number. If you plug this in the calculator, something around 0.69. And then if you do it with e, you will not just get any random number. So if we did the exact same calculation with e, I'll just, so let's say we were using e to the x as instead of 2 to the x. Remember, e is just a number. Turns out it's around 2.7. So you just imagine about 2.7 to x. Okay, so if x is 0, then, so our first point can be x equals 0. E to the power of x is equal to 1, right? Because any number to the power of 0 is 1. You can get that from our properties, or if you already know raising stuff to powers. Okay, so x equals 0, e to x equals 1. Remember, the whole goal here is to find the sensitivity of the output relative to the input. It's like, if you imagine, the way to think of it is, if I'm changing the input, whatever the input is, I'm varying it. Started at 0, maybe I'm varying it like 1,000th or something. We want to measure how much does the output change relative to that amount. Not the total change, but the total change relative to that amount. Because otherwise it's going to be basically 0. Right? So it's all about the relativity, like how much more or less. You have to compare them. Otherwise it completely depends on basically how much your input changes. Because your output, how much your output changes completely obviously depends on how much your input changes, but the ratio in between them is something special. Right, like that's not going to just be completely dependent on like how much your input's changing. It might be some cool value. Okay, so if we do the same calculations, another point we choose, I don't know, x equals 0.001, and e to the x, well, would just be e to the power of 0.001, because if that's the value we choose for x. So now what we do is we figure out in between these two values of x and their, so how much did the input we were putting in change from 0 to 0.001. That was a change of 0.001. And then how much did the output change? The output changed by, well, we went from e to the power of, we went from 1 to e to the power of 0.001, so that we subtract them, we get, it changed by e to the 0.001 minus 1. Okay, so now what we need to do is we need to, remember, this is, so what we have, that the amount the input changed, very small, and the amount the output changed, which is also pretty small. So what we need to do is we need to divide them to figure out how much, basically, how much the output changed relative to the amount we changed the input. It's like how fast the output is changing. But it's very important you take the ratio between them, right? You may eventually calculate, see the notation dy dx. you have something super small, dy, it's like the change in y, divided by the change in x. They're both basically 0, but you have to divide them. That's very important. Anyway, so here, if we divide these two things by each other, what we have is this is the change in our output, this is the change in our input. So to find how much our output changes versus how much our input changes, we just use division. So I'll write that down, and we get e to the 0.001 minus 1 over this thing, and you can plug this one into the calculator, remembering that e is a number around 2.7, and you'll get that number, and you can look up the exact value of e. But if you use the exact value of e into this equation, you'll get a number that's pretty close to 1. And what does the 1 represent? It means that the ratio in between how much the input and output are changing is 1, which means the input and output are basically changing by the same amount. Okay, now this is big, right? It's not just, there's not some random. So this is what's special about e. And another thing you might notice if you're very astute, I think that's a good word, is that it's not exactly 1. And the reason for this is what I said earlier about you have to use an infinitely small value. Since we just use 0.001, it's close to exactly 1. They're close to being exactly the same, but calculus likes smaller numbers or smaller changes. So the smaller change you use, if you use a smaller number, the better and more accurate it would be. But if you used a quote-unquote infinitely small number, it would be exactly 1. Meaning that, in a way, e is a special number such that e to the power of x, if you're looking at 0, so you set x to 0, then the amount x changes from 0, if you're doing a super small amount, is basically equal to the amount e to the x is changing from 1, which is this value at 0. So you set x to 0, e to x is 1, you change x a teensy tiny bit, that's a very good, it's very, very close to the amount e to the x is going to change. So they're basically, the changing amount is the same. And the smaller the amount, the closer they'll be. The closer the ratio will be. Okay? So that's the number e. You can define it as a number that has this property. I'm not going to prove that there is a number with this property, but you can prove it basically by looking at numbers and saying, oh, there has to be something in between or stuff. You can do stuff. Anyway, that's the first part of my video. Thanks.